pleased to be able to introduce two important people to you. The first will be Professor Dan Cziczo, the Vincent P. Starr Associate Professor of Atmospheric Chemistry at MIT and a winner of a Presidential Award for Science. The second person is a surprise, who I'll introduce at the end of the program after the Q&A with Professor Cziczo. When we began the Energy and Clean Tech series 11 years ago, it was clear to us that there were multiple reasons to pursue clean technology: national security, energy independence, financial health, pollution reduction among them. And while we held a few early events on climate change and water, we focused mostly on technological opportunities for new companies, new products and services. We attracted a good audience, and we spun off and founded the California Clean Tech Open, some of you may be aware of, with some of our members. And I think we fostered a growing interest in the field of clean technology. However, looking back on the last 11 years, it's actually surprising how little has been accomplished in the field of clean technology, as much more than maybe has been done. It's surprising how little has been done. And there's been a surprising debate about the impacts of human pollution in the air, on the land, in the water, and in the ocean, and on the climate in general. So we feel it's timely to present a series on the driving forces behind clean technology and the issues that are related to human pollution. And now we're continuing a series that started with an overview by Kerry Emanuel on the issue of climate change. Tonight we delve into atmospheric causes and effects. We'll have an event in a few months on the oceanic aspects of climate change. And then we'll follow up with economic and policy events sprinkled over the next couple of years with our regular events on various aspects of clean technology. For tonight's event, we're pleased to have with us Professor Cziczo, who is a noted cloud chaser, and you'll hear more about that. While we all breathe it, most of us do not understand the dynamics of our atmosphere, nor the changes it's undergoing. So we welcome this opportunity to have Dan inform us about the current situation, and in addition to telling us of some surprising discoveries, he's going to do a magic trick. So, Professor Cziczo. Maybe that's it?
That's it.
Okay. Well, I'll let you start it.
Thank you, Greg.
Okay. Good luck.
Perfect. Well, I'd like to start by saying thank you to a few folks. Greg, as well as Doug, for setting up this invitation to come out and get a chance to speak to you about what I do tonight. And I also wanted to say thank you to Ralph Bruckler. I had the fantastic opportunity to meet Ralph and his wife Wendy, as well as Mike and Pam Crane, who are members of the club here. And Ralph is the one responsible, I think, for putting my name forward as somebody that might be able to talk in this series. And it's a little bit daunting, I have to admit, to follow up Kerry Emanuel, who's sort of growing up was one of my heroes in this area. But I hope I can add something. And what I'd like to talk to you guys about tonight is the role of the atmosphere in climate change. And so I always, when I get a chance to come out and talk to an MIT alumni group, I sort of think about the story that I want to tell about the research that we're doing and what we've learned. And so I like to put it in sort of a book format. And I thought I'd start out with something like a preface here and just tell you a little bit about myself, how I ended up at MIT and what I do, what my group does. And then there's sort of three chapters that we want to go over this evening. The first one is, I think, common. Most of the folks in this room have probably heard about climate change. You probably know a little bit about it. And so we're going to talk about the basics to get started. We're going to delve a little deeper, and this is my favorite part because this is what I really do, is what's the role of particulate matter in the atmosphere, and how does it affect clouds, and how are clouds affecting climate? And then we're going to move into the future and talk about a topic of geoengineering, which is maybe something, it's one of these buzzwords nowadays. It's something that you may have heard about in the news, you may not have heard about, but it's something that you're going to be hearing about in the next few years. So we'll talk about that. And then Greg mentioned the topic of cosmic rays being of interest to some of the folks in the group here. So this is sort of supplemental reading. I couldn't quite fit it in before people are going to want to get out of here and go for dessert, I think, at some point. But if you are interested, I have some slides in backup, and hopefully you'll come forward and we can go sort of through the supplemental reading. So with that said, I'm just going to start out with a quick preface. And I wanted to tell you how I got into this field, and it's very circuitous. I actually have an engineering background. I started out in aerospace engineering, of all things, and worked in California, actually. I was at JPL down in Pasadena. And I started out working on this guy here. This is, for those that are into space sciences, this is the Galileo probe that went to Jupiter. And I worked as an engineer doing orbital mechanics for this, trying to figure out where this probe was going to go. And I had the opportunity to start working with atmospheric scientists. So they were the folks that were interested in all of the little experiments that were going on this craft. This is one that's pointing towards the atmosphere of Jupiter, so I picked it on purpose because they're doing atmospheric sampling. And so I was responsible for making sure that we still had fuel on this spacecraft, that we could fly around for a long time. And it frustrated me to no end that the scientists wanted to point these instruments all kind of ways and that you would have to use up fuel on this spacecraft, until I started to realize that was the purpose of the spacecraft. And so I thought that I would stay at JPL. I thought that I'd go and get a doctorate in atmospheric sciences and start to get into this part of the field at Caltech. And then on a fateful trip back to Chicago to see my family at Christmas time, I went to the University of Chicago and met John Abbott, who would become my future advisor. And he was just sort of finishing off some projects on the polar ozone hole, and we were starting to get interested in climate change. And he started talking about particles in the Earth's atmosphere and how they were forming clouds. And I sort of knew about clouds from Jupiter, and I got really intrigued in this and thought that this was just a fantastic project and a neat way to spend my graduate career. So I built this little doohickey right here, which is a chamber that we studied clouds and particles in. And I was a laboratory scientist for 4 or 5 years, and it got the bug out of my system of getting my hands dirty and working in the laboratory. But I found that at the end of my PhD, I still had this itch to get into the atmosphere, to use my aerospace background. And so most of our work now is involved in building new instruments, going out into the atmosphere and sampling the particulate matters that's there, sampling the clouds that are in the atmosphere, and understanding how human activities are changing the particles, changing the clouds, and what that impact is on atmospheric science. So after a number of different stops, including the chance to go to Europe for a few years, I finally ended up at MIT about 3 years ago. We have a wonderful group there doing some really fun experiments. I'll try to tell you about some of those over the course of the night, and then in the conclusions this evening, I'll show you who I've got a chance to work with. And some further connections. I'll bring the connections back to the Bay Area at that point. So with that out of the way is sort of, maybe that isn't even the preface. It's sort of like the little dust jacket that they have on a book where they introduce the author. It's the introduction to the author. I'd like to start talking to you guys about climate change this evening. And so any talk about climate change really has to start out with the sun, because that's where all of the energy to drive the Earth system comes from. And folks probably learned this very early in college or maybe in high school, that the sun is giving off a great deal of radiation. It's radiating out into space, and it's striking the planets around it. So this is, for example, Venus. That solar energy comes out. It impacts on the planet. It heats that planet up. That planet doesn't just keep receiving that energy. It absorbs that energy. It warms up, and then it starts re-radiating energy back to space until it reaches some type of an equilibrium. And to understand that, you can think about our two nearest neighbors. In the solar system, Venus is slightly closer to the sun and receives more energy. Mars is slightly further away, receives a little bit less energy, and the Earth is somewhere in between. And you can do a very simple radiative transfer calculation. You can think about the energy that's being given off. You can think about the sun, or the Earth receiving that energy. You can find out what kind of equilibrium state that would be. It's the simple Stefan Boltzmann law, which a lot of us learned as freshman physicists. And you do that calculation, and you find out that the Earth should be below freezing. And at this point, you think that atmospheric scientists are crazy and that there's something wrong with all of our calculations. But that calculation doesn't take into account the atmosphere of the planet. And the atmosphere of the planet is very, very important because it contains greenhouse gases. Those greenhouse gases act as a blanket. What I mean by that is that the atmosphere of the Earth has these species that will absorb that outgoing radiation, that heat that's coming off of the planet. They absorb that energy, and some of it gets radiated into space, but some of it gets turned back around and fed back into the planet. And it's just like laying down on a bed on a cold winter night, and you're sort of cold, you throw a blanket over yourself, that blanket warms up, it re-radiates some of your heat back towards you, and it keeps you much warmer than you would be without that blanket. The blanket itself is not creating any heat. It's not adding heat to the system. It's just absorbing the energy that you're putting into it and keeping some of it in the system. This is the same thing that the Earth's atmosphere does for the planet. So instead of being below freezing, the temperature of the Earth is something on average like 15 degrees C, something on the order of a chilly day on average. And then you sort of look for examples of too little or too much greenhouse gases to our nearest neighbors in the solar system. And you can look at Mars, and if you do the simple radiative calculation for Mars, you find out that Mars should be something below freezing, below 0 degrees Fahrenheit, that is, something like -10. And in fact, the temperature of the planet is very close to that. And the reason is that it has a very thin atmosphere. It has very few of these greenhouse gases. It doesn't have an effective blanket, so the temperature is right what you would predict. You go to Venus, which is a little bit closer in. It has, you do the simple calculation for Venus, and you find out that it should be quite warm. It should be sort of like a hot summer's day, maybe something like 100 degrees. And instead, the temperature of Venus is warm enough that it can melt lead on the surface. And the reason is that it has what's known as a runaway greenhouse effect. It has so many greenhouse gases in the atmosphere, it traps so much heat, that the temperature of the planet is much, much higher than you would predict. So high, as I said, that you can melt substances like lead on the surface. And so you would think that the story would sort of end here, that the Earth had found some type of equilibrium. It receives the sun's energy, it re-radiates heat, there's greenhouse gases, and everybody's happy, and the temperature stays quite stable. The problem is that we, through human activities, are adding more and more of these greenhouse gases to the Earth system. So we've forced the planet out of equilibrium. And to show this, you can think of a plot of the temperature of the planet and what's happened to it over the recent years. And so what we find is that the warmest years on record, and I should mention that I'm counting the warmest years since about 1880. 1880 is one of these magical years when we believe that thermometers became accurate enough that they're pretty similar to what we're measuring today. So we take temperature records, like if you listen to the evening news, you'll often hear, it's a record warm day. Well, that's not going back, to the beginning of time or something. It goes back to about 1880 when we feel that thermometers were pretty accurate. But if you look at the warmest years since that period of time, the warmest on record, all are in the years 2000 and the 1990s here. It's actually pretty striking to me that on this list, which was compiled in about 2010, that to get outside of my lifetime, you have to go down to number 22 on the list. And to get outside of sort of my parents' lifetime, you're actually not even on the list here. This record can actually be updated. And what we find is that 2010 actually replaced 2007 as the warmest year on record. And then since then, 11 was number 11, 2012 was number 10, 2013 was number 4, and 2014, despite the cold winter that we had in the Boston area, is actually shaping up to be number 1 so far. At least through May, it was the warmest year on record. And so this is a symptom, this is a side effect of this increase of greenhouse gases, the human addition of greenhouse gases to the atmosphere, forcing the Earth system out of equilibrium and warming the planet. So that globally right now, over land at least, we're about 2 degrees warmer than we were before industrial activities took place. We live in a very different climate system now. Our kids and our grandkids are going to be living in a very different world than the one experienced by our parents, our grandparents, and before them. So again, if you watch the nightly news, you might think that there's a huge debate on this and that we're just figuring this out right now, that we haven't really understood this before. But actually, this was all worked out over 100 years ago. So there's a very smart scientist. This is Svante Arrhenius. He was a Swede, and that'll become important later in the talk. And he wrote this fantastic paper. It says, if the quantity of carbonic acid, by that, this is the old term for CO2, increases, that you'll see that the temperature of the planet is going to increase. He says nearly an arithmetic progression. What he worked out was if you increased CO2 in the Earth's atmosphere, how much warmer would the planet get? This is something that we now commonly call climate sensitivity. Increase in CO2 translates to some increase in temperature. And he thought for a doubling of CO2, which we're very close to at this point, you were going to increase the temperature of the planet by something like 3 to 5 degrees. So this is, joking aside, this is not new. This was something that was worked out over a century ago. There's really no debate about the effect of greenhouse gases and their increase in the Earth's atmosphere. And one of the things I told you is that I love laboratory work. I love getting my hands dirty. And so one of the things that I love about the Arrhenius paper is that it's based on laboratory work. He's not just sort of making some supposition or trying to figure out how molecules might interact with heat. Instead, it was based on the earlier work of John Tyndall, who was a Brit, who built this funky little chamber right here. He was able to put different substances into it, expose it to different types of radiation and heat, and see what the materials inside of this little tube that he'd built would do. And he was the first one that worked out that CO2 was a greenhouse gas, that if you exposed it to infrared radiation, the heat that's coming off the planet, that the gas could trap some of that heat and then re-radiate it, that this tube here would warm up. So I always find this stuff to be fascinating, sort of the history behind how experiments were built. So this is sort of the end of chapter 1. And for those of you that ate a little bit too much at dinner, I thought I'd put the Cliff Notes version of this up on the board. So the major points that I want to get across here are that greenhouse gases, mainly carbon dioxide. There are some other ones. The second most important one is methane. The third most important one is nitric oxide. Things that human activities are putting into the atmosphere warm the Earth because they're trapping the outgoing heat that the planet is trying to radiate away. The other thing that I want to get across to you is that this is not new. This is not controversial science. The laboratory experiments for this were worked out in the 1800s. The understanding of climate sensitivity to greenhouse gases was worked out by about the year 1900 by these two folks here. So I think knowing this group and some of the folks in it, this is probably fairly repetitive to you. You've probably seen a lot of this before. You've probably heard about greenhouse gases, and you may have heard about some of these folks that were doing the early work in the field. What I hope Chapter 2 is going to be is a little bit new to you. It's something that I work on that I find very near and dear to my heart, and this is the effect of particles in clouds on the atmosphere. So when I did the very brief overview of the sun's impact on the planets around it and they're heating up because of solar radiation, I used this image, which is courtesy of the Japanese Space Agency, and it's actually a real image of the Earth. What they've done intentionally is they've stitched a number of photos together, so you get this beautiful view of the planet, and it's completely unrealistic for what reason? Yeah, there's no clouds. This is just not what we normally see. So on average, this is what the Earth looks like. I mean, it's covered about 30% to 40% of its surface area on a given day by clouds, and these have an incredible impact on the radiative balance of the planet, as well as the greenhouse gases that are in the atmosphere. So there's this very famous report called the Intergovernmental Panel on Climate Change report. This is the one that just came out at the end of last year as well as the beginning of this year. These are put out every 5 or 7 years. The last one is probably the most famous one. It's the one that won the Nobel Peace Prize along with Al Gore for their work trying to understand climate change. And if you give an atmospheric science talk, you have to put this figure up. It's sort of like the obligatory figure that you need to do. It's trying to distill the whole report into one figure. And so what the authors did here is they sort of set this vertical bar right here. And everything that falls to the right is something that warms the atmosphere. The columns are different things that we as humans, different effects that we as humans are having on the atmosphere. Things that fall to the left might be somewhat surprising, that there's things that are going on that are actually cooling the atmosphere, as well as the greenhouse gases that are warming it. So what this report says, for example, is that there's a number of greenhouse gases. We mentioned CO2 as being predominant, methane, nitrous oxide falling into the other greenhouse gases. These have a large warming on the atmosphere. And this is separated from the 1950s to the 80s to the 2000s. So you see that we're increasing these as we go through time. We're burning additional material, we're burning additional coal, additional oil, more and more CO2 going into the atmosphere, more and more of a positive effect over the decades. What I think is surprising to a great deal of folks is that there are negative things. There's things that appear to the left of that bar, things that appear in blue here. These are labeled the direct effect and aerosol impacts on clouds. So I'll try to translate science speak to the crowd here. The direct effect is particulate matter that's put into the atmosphere. So you guys can go out on sort of a hazy day or a smoggy day, and you'll notice that there's particles that are being put up by human activities. For those of us that were driving around today, if you get behind that truck that's belching out clouds of black carbon, it's pretty easy to see that humans are putting particles into the atmosphere. What this is saying is that the dominant effect of particles is to scatter more solar radiation back into space. And I'll show some pictures of this in just a moment. But by doing this, it's cooling the planet. It's not allowing some of that sunlight, some of that heat to make it into the planet, instead taking it out of the Earth system before it even gets there. The second bar here, the aerosol impacts on clouds, is a little harder to understand, but this is the magic trick that I'm going to do in a few moments. What this is saying is that at the heart of every cloud droplet or every ice crystal that's in a cloud, there's an aerosol particle. There's a particle that's in the atmosphere. And some of these particles have been put there by human activities. So by creating more particles and putting them into the atmosphere, we're responsible for some of the cloud formation that's going on around the planet. So if we go back to our image here, it's saying some of these clouds, if we went back to a pre-industrial Earth, wouldn't be there. They're only there because we're putting the seeds for those clouds to be there. And these two effects, the particles we're putting in and the clouds that we're putting in, are leading to a net cooling. You'll notice that these aren't as big as the greenhouse gas bars. They're not taking away the warming. They're not offsetting it. They're just taking away a bit of it so that the net effect here is still large and positive. But for the MIT folks in the crowd, you were probably trained to look at error bars quite a bit. And the first thing that you'll notice here is that the greenhouse gas forcing right here has this really little error bar on it. It might be this big, it might be this big, but it's really close to the value that's given in this report. It means that we understand greenhouse gases really well. It means that we understand how much is being put into the atmosphere, and we know what the effect is on the atmosphere. And it really goes back to Arrhenius and Tyndall. It's something that's been studied for over 100 years now. You look at the aerosol effect, the particle effect, and the cloud effect, and you'll notice that they're negative, but look at the size of these error bars. They're much, much greater than these here. And this translates to the total human effect. They're using the word anthropogenic here for human effect. The total anthropogenic effect here is positive, but it might be very small, it might be relatively small, it might be relatively large. This error bar is these error bars here. It's not the greenhouse gases. Our lack of understanding in climate change, the real uncertainty in climate change, is not about greenhouse gases. It's not about CO2, methane, or nitrous oxide. It's what are particles doing to scatter solar radiation, and what are particles doing to affect cloud formation. So if you're having a hard time thinking about this, you probably haven't spent much time in Southern California. But actually, I really like this image. So if you remember the news, about a year ago, this was actually about June the 15th or June the 16th last year, there was a huge particulate matter problem in Singapore. And this is an image of it. So this is Singapore. There was a great deal of biomass burning going on nearby. Folks were burning land to create arable land or changing forested land into irrigatable land that they could put crops into. And so this is smoke from nearby biomass burning. And I don't have to probably tell you folks about that. I'm sure you see wildfire burning go on a yearly basis. Huge smoke plume over the city. And I like this as a demonstration tool just to make you think about all of the particulates that are here. This is not fog. This isn't a cloud that's at the surface. This is just particles from biomass burning. You can think of the sunlight that's coming in and the fact that a lot of that sunlight is being radiated back away. I mean, you can actually see it in the image. The fact that this is so blurry is light coming in from the sun that's being scattered to you, in this case, the lens of the camera that's looking at this. It's light that's not able to go down to the surface of the planet and warm the planet up. So this is the so-called direct effect that you see in that plot. The cloud effect is a little bit harder to understand, and that's why we're going to have to do a magic trick. The idea behind clouds is this. In a pre-industrial atmosphere, there were a certain number of particles that were made and they were put into the atmosphere naturally. You can think of them as being particles from sea salt or dust storms or natural wildfires. And so these very few particles were spread out and they were exposed to water vapor. Water vapor reached a relative humidity of 100%, and we know from the nightly news that when the relative humidity hits 100%, we're in for a rainstorm or a snowstorm. So these particles picked up that water and they created little droplets. Now, if we translate that same cloud and we put it into an industrial atmosphere, there's a lot more particles in that case. There's the same amount, or almost the same amount of water vapor, but it has to spread itself out over many, many more particles. It means the droplets themselves are much smaller. More particles to spread out over smaller droplets, same amount of water. We know that the optical properties of many more smaller droplets is to make a cloud more reflective, more white. So the pre-industrial cloud would look very gray. This is the sort of cloud that you might see before a rainstorm. You see clouds get very dark. They look very ominous. That's what the cloud would have looked like. The post-industrial modern-day cloud is going to have water spread out over many more sites. It's going to be much whiter, much higher reflectivity. And so this is where I'd like to do my experiments. I'll put this down for a moment. And we've got a cloud chamber over here. Actually, I'll take this with for the next part. So we're going to make a cloud. So I like this image because it sort of has an ocean in the background, and you can think of this as being a cloud that's forming over the sea. And we're going to do the same thing in here. So I'm going to make you an oceanic cloud. I'm going to bring these two things of wildfires and ocean clouds together in this demonstration. The way that clouds normally form in the atmosphere is you get a bit of heating at the surface. And as you guys know, especially living so close to the Central Valley, the Earth warms, you get uplift of that air. The air starts moving upwards. That air is going to cool off as a result. The relative humidity is going to get somewhat higher, and you're going to form a cloud. I think when I give this demonstration, a lot of people don't often think that particles are really responsible for clouds, and so that's the first thing that I'm going to try to prove to you. So this is my demonstration. This is going to be our air over the Central Valley that's going to, in this case, we'll say that it's going to move over a lake or over the Pacific Ocean. And I'm not quite tall enough to raise this up fast enough to cool it off. So I've got this little vacuum pump on the ground. And what that's allowing me to do, the folks in the front row can probably hear the hissing sound. So the pressure of this jar is dropping. And so by doing that, by putting my finger over this, we're going to pretend that this is dropping in pressure. It's raising up in the atmosphere, and we're going to form a cloud in it. And right now you're probably skeptical and saying, well, he's doing that and there's no cloud forming, so what's the point in this demonstration? And the reason is that I got in here a little bit early, first off to make sure that this demonstration actually worked, but second off to put this little filter on it. So what this filter is doing is it's taking all of the particles moving into this jar out before it gets there. So this is completely particle-free air, and you can see I can put my hand over this. For those in the front row, you can hear when I take it off, it hisses pretty loud for a minute as it tries to get back to the atmospheric pressure in this room. And so what I'm demonstrating here is that without particles, we can't form a cloud in this jar. Okay, so we need to make some particles. I'm not going to light up a cigarette. Instead, I'm going to break out a match, and we're going to use this to simulate one of those wildfires, like the one that you saw in Indonesia and Singapore last year. So that's the wildfire. We're going to do it once more. I actually thought I have 4 matches, so hopefully I don't do that 3 more times. This is going to be the wildfire. So this is going to be like the crops that are being burned, the forest that's being burned to create this, this arable land that they want to farm. So I'm going to do that, and the smoke's going to go inside. And I'll cover this up. And can you see in the front row that we just formed a cloud on that? I'm going to use one more just because I want to get some more particles in there so that it looks a little bit better. Hopefully that one will turn out darker. That one's a little bit better. So now, thank you. That's the magic trick. So we can even let that go away. We can put our finger over this again and make this parcel go back up in air. And even though it looks like the particles have gone away, they're so small and they're still hanging around in there, even though I'm still pumping them out and letting clean air in, that we can repetitively make more and more clouds in here. And it's hard to see, but as we go to lower and lower particle concentrations, this actually gets a bit more gray. The reflective properties, the optical properties of these particles change as we allow them to pump away. It gets a bit darker. Maybe you can see that in the front row, right there. So that's my magic trick. If you were expecting more, I'm sorry. And this is the type of work that we do in the lab at MIT. Except that we don't use that jar over there, except when we have students come by for a visit. These are the type of cloud chambers that we use in the lab at MIT. These allow us a much more precise control over the temperature. In this case, we were fixed to room temperature. They allow us a much more precise control over the relative humidity, the amount of water vapor that's there. In this case, it was 100% relative humidity to start with, because you'll probably have noticed that I put a bit of water to sort of help form the clouds in there. This is one of the cloud chambers that we use. This is a partnership with a small company that we were able to build this. This is now commercialized, so people can take these out into the field and make measurements at different locations, so that, for example, we can understand human effects on clouds not only in Boston, but in places like the Southern Hemisphere. They're very portable. You can take them everywhere. This is a cloud chamber that's even more precise. It is unfortunately not portable. This is an old nuclear reactor in Germany that was retasked to make a cloud. And instead of a cloud chamber that in this case is about 6 feet high, you'll notice these are different floors here as you walk up, and the cloud chamber is behind this wall, and it's sitting in sort of a thermos area. It's very precisely temperature controlled. There's a number of pumps in the bottom of the floor, which I have to tell you are much larger than the one that's right there. So this is the way that we're trying to get at understanding cloud formation, the effect of human-emitted particles on clouds in the Earth's atmosphere. So this is the work that we're doing, and so if I had to do sort of a Cliff Notes version of the second chapter, what I'd like to say is that particles and clouds scatter more sunlight than they absorb or trap heat. there's certain particles that actually do absorb a bit of sunlight. Black carbon is one that you may have heard about in the news as creating, as trapping sunlight and creating heating. But the vast majority of particles are not black carbon. They're sulfates, they're organics, they're things like material made from wildfires. They're scattering a great deal of solar energy back into space. The net effect of having more particles from human sources, from emissions from people, and the clouds that they spawn is therefore a cooling effect. But the important thing here is that these particles and clouds represent the most uncertain aspect of climate change. So again, just to reiterate, it's not our lack of understanding of greenhouse gases or CO2, it's our lack of understanding of the particulate matter that's being put into the atmosphere, the clouds that are being formed. That's the real thing that we don't understand. So again, the first chapter is something that you probably have read before. The second chapter hopefully was a little bit new, and it tells you a little bit about what we're trying to do at MIT right now. The third chapter is something that I think maybe I can get a show of hands. Has anybody heard of the term geoengineering? There are a few? Oh, wow, okay, it's actually the majority of class. So geoengineering is something that you are going to be hearing, even for those that are very well educated in the room that have heard about it. It's something that you're going to hear more and more about as we move into the future. So it doesn't probably take a genius to think of this, so I've just said that aerosol particles that are put into the atmosphere by human activities and the clouds that they form are cooling the climate, but that they're not cooling as much as we have warming from greenhouse gases. So it probably isn't a huge leap to think that somebody thought up the idea, well, if a few particles are cooling the climate a little bit, maybe what we should do is intentionally put in a lot of particles into the climate, and that's going to offset perfectly the amount of global warming, the amount of greenhouse gas warming that's going on in the environment. And this is the heart of geoengineering. This is what's being proposed by a great deal of people right now. You'll notice that I like giving the historical aspect of this. So geoengineering is not something that just got thought up a few years ago. It's not something that was just proposed because of climate change. And like many great things in science, it actually owes its roots to science fiction. So geoengineering comes from the concept that was thrown out in a science fiction book called Collision Orbit in 1942, of a concept called terraforming. So in the 40s, people were starting to realize that there were other planets out there around not only in our solar system, but possibly planets around stars in other solar systems. This wasn't proven until the 90s, but of course people were talking about it in the 1940s. And the thought was that, well, what if we find a planet that isn't quite right for human habitation? It's a little too hot, it's a little too cold, it's not this, it's not that. So maybe we have the technology to actually change the temperature of that planet. And this was something that was put together for Mars, that people had proposed putting very effective greenhouse gases into the atmosphere of Mars that would raise the temperature and allow for human habitation there. For those of you that like classic science fiction, you'll notice that this was actually really probably first proposed by H.G. Wells in War of the Worlds before the turn of the last century. Except in War of the Worlds, if you're familiar with it, the idea is that Martians are going to Mars-form the Earth, if I can make up a word, so that it's habitable to them and not habitable to us. So geoengineering is just simply an extension of this idea of terraforming. But the concept is that we're doing something to the Earth system that is not good for the Earth. So we're going to do something else to change it back to a state that we want to live in. And the one that we're obviously talking about today is global warming, heating the temperature of the planet up via greenhouse gases, and then trying to do something else that's going to bring that temperature back down. This is generally attributed to Paul Crutzen, who wrote a paper on this topic of geoengineering in 2006. And what he suggested was that we could put more particles into the atmosphere. And I'll talk to you more about this in a few minutes. And this geoengineering concept being attributed to Paul Crutzen kind of makes sense because he won a Nobel Prize in chemistry a few years earlier, so people tend to pay a lot of attention to Nobel Prize winners. But there are actually several earlier proposals for this. So the first geoengineering proposal actually looks like this. Does anybody have an idea what this is? I heard lava. It's actually something different. It's a coal seam fire, absolutely, yeah, gold star. So this is a coal seam fire, a coal fire that was unintentionally set. This happens to be in India. I don't want to give you the idea that this only happens in other countries. There's one that's been burning in Pennsylvania since the 1960s, actually. And these liberate a great deal of carbon dioxide into the atmosphere. So you're probably wondering, why do coal seam fires and geoengineering have something in common? So our buddy Arrhenius, who was a Swede back before the turn of the last century, came up with the idea. He was doing his carbon dioxide experiments because of geoengineering. Sweden is rather cold. So what he wanted to do was have a climate that was much more like Central Europe. So Arrhenius was looking at carbon dioxide in terms of a greenhouse gas because he wanted to warm Sweden up. If you read his papers, I'm not making this up, what he proposed to do was set coal fields on fire to liberate so much CO2 that you could change the temperature of the planet by 3 to 5 degrees, because he felt that was the temperature difference between, say, central Germany and Sweden. So you would move the grain belt of Europe up into Sweden. This was really his proposal. So this was sort of the first concept of geoengineering. It was completely contrary to what we would think of today. It was creating greenhouse warming in order to change the climate to the benefit of one country. So it didn't sort of skip from Arrhenius in the sort of turn of the last century time frame to today. Instead, we have thought about this as a country for a great deal of time. So this is a report, Restoring the Quality of the Environment. You'll notice that the presidential seal is here. And so this is a quote from that paper: climatic change may be produced by increasing CO2, in other words, greenhouse gas forming, possibility of deliberately bringing about countervailing climatic change, in other words, doing geoengineering, finding something to offset greenhouse gas warming. So this is something that was considered by the president. Again, you might think that at this time politically in the United States we haven't reached a consensus if climate change is actually happening, much less that we need countervailing technologies. If you can see right down here, the date on this report is November of 1965. So yeah, this has been around for a little while, and I actually thought my thunder was a little bit stolen, because if somebody read the New York Times today, they were talking about how the Nixon administration was talking about the need to adapt to climate change in the late 60s and early 70s. So what I would like to express to you here, this is not a Cliff Notes point, I won't put that up at this time, but this is not new. Greenhouse gas forcing is not a new concept, neither is this idea that we might want to not stop burning greenhouse gases or making greenhouse gases via burning fossil fuels, but instead that we might want to do something else so that we can keep burning those fuels, keep producing greenhouse gases, but keep the temperature of the planet where it's at. We're talking about it as a nation several decades ago. And so there's a number of different ways that this has been proposed. And they roughly fall into two categories. This is a nice figure. I hope you can see it here. It's from New Scientist. So if anybody wants the slides afterwards, I'm happy to give them. And I'm trying to put the attribution to all of those. So they break this up into a couple of different ideas of ways that you could do this type of work. And one that they suggest is a number of ways that you could capture carbon dioxide. So carbon dioxide is being put into the environment as the predominant greenhouse gas due to fossil fuel burning. And maybe there's some ways to capture it. So one big one is just that you put something on the end of a power plant or the end of a car's exhaust system, you capture the CO2. And folks have been working on that. That would probably be the most simple. There's other ideas. For example, you can offset your carbon by buying trees and allow trees to grow, capture some of that carbon. One of the keys is that if these things die, they have to be put and sequestered in some way. They have to be trapped so that they don't release that CO2 after they decay back into the environment. But I would contend that carbon capture is not really geoengineering. It's just not doing or doing less of what is putting greenhouse gases into the atmosphere. And it's often confused, and it was in this case by New Scientist, as being a geoengineering method. It really isn't. The geoengineering methods are really doing something else that's going to offset the CO2 greenhouse gas warming potential. And those things that are proposed are, for example, to put particles into the atmosphere or to create artificial clouds that can reflect sunlight back into space. And so the dominant one that I want to talk about today is actually taken from a natural example. So this was a picture, the paper itself that it appeared in is 1998. This event took place in 1991. This is the Mount Pinatubo eruption. So you can see the eruption going on. Mount Pinatubo is here. And this is material being ejected by the volcano. And I love this photo for scale because these clouds are sort of punching up to the top of the troposphere, the layer of the atmosphere we live in. You get a sense for how powerful this volcano is. This is material that's being blasted right past where traffic would take place into the stratosphere, the next layer of the atmosphere up. And that's very important because those particles, once they make it into the stratosphere, can be very long-lived. It's a very stable part of the atmosphere. Those particles, once there, hang around for a year or two in time. And this was seen by a number of satellite images. So these are optical depths, amount of aerosols from before the volcano to a couple years after the volcano. And you can see this little red mark here sort of spreading out, and they're all centered on where the volcano took place right here. So this is aerosol being injected into the stratosphere, spreading out towards the poles in both directions. I talk about this in one of the classes that I teach at MIT, by the way, and I asked the students in the class if they remembered the Mount Pinatubo eruption, and they told me that no, they weren't actually born at that point in time yet. And I resisted the urge to fail them for telling me that, but nonetheless, some of us in the room actually remember this. There's other students that don't, that would be in the same age bracket, but you'll have to take my point on this, that this was pretty powerful. It was in the news for quite a while, and it had a huge impact. The impact that we're most interested in for this lecture is the temperature impact. If you remember, the year after the eruption, 92 and into 93, the temperature of the planet was somewhat lower. You didn't see these years end up in that top 25 list because they dropped by about a degree in temperature. These extra aerosols that were put into the atmosphere were reflecting sunlight back into space, and you saw this precipitous drop in temperature. There's been other volcanic eruptions in human history, some of them as recently as the 1800s, Krakatoa, for example, that dropped the temperature of the planet for a period of years afterwards by up to 3 or 4 degrees. There's reports of the canals freezing in northern Europe as a result. Does anyone know the famous picture, Munch's Scream, where he's got the face and the crazy background of sunset? That was actually painted after the Krakatoa eruptions. That was the crazy sunsets because of all of the particles that had been put into the atmosphere as a result of those volcanoes. And there were years that they talked about crops being lost, summers being lost because of the temperature change. So this spawned many attempts or many ideas about geoengineering. So one way to talk about this is the so-called volcano method of geoengineering. And it says that, say we want to offset that global temperature rise of something like 1.5 degrees Fahrenheit, you say that the Pinatubo eruption was on the order of about 15 teragrams of sulfur, in this case sulfur dioxide, that turned into particles. So what we would do is, this translated to about 0.75 degrees of cooling. So maybe what we do is we dump in about 20 teragrams intentionally to the same part of the atmosphere. And then every year as that sort of falls out, we'll just put 10 teragrams more into the atmosphere. This sounds like a ton of material. It's actually not. This is very, very doable. It's been proposed to do this via aircraft. It's been proposed to do this via balloon. And there's even other designs that are going on. This is the so-called garden hose method. These are wings that would fly in the stratosphere. This is essentially a garden hose. And they're pumping sulfuric acid out of this garden hose, which is actually not sulfur dioxide, but the more direct form, and making little particles that are going into the stratosphere. And people have actually been working on the engineering of this. One of the things that I've paid attention to over the last few years, as this has gained some traction, is that geoengineering is now very infrequently used by the folks that are suggesting this. It's somehow become a nefarious word. It has dark meanings, like you're going to do something that's going to be bad to the planet, which in some way you are. And so they've started to settle on the term solar radiation management, or SRM, that we're going to control the amount of sunlight coming in. And for somebody that remembers when we used to use the term torture and then turned it into rendition, I sometimes think that there's scary parallels between geoengineering and solar radiation management. So I think Greg actually gave me the advice that if you're going to put up an acronym, you better define it. If you guys see in the news that somebody's talking about doing SRM, what they're talking about is doing geoengineering. They're talking about pumping material into the stratosphere in order to offset global warming. So I'm going to put down my advancer for a moment, and so I wanted to have some audience participation. I know you guys get to ask questions afterwards, and I'll try to answer them. But I wanted to ask you guys some questions now. So I've been joking around, and it should be pretty obvious that I'm not a big fan of geoengineering. I think that there's some serious flaws with it. But I want to ask you guys, let's do a risk versus reward talk. What would be the rewards? And let's be fair about this. I mean, global warming the climate change that we're seeing is having some deleterious effects on the planet. So maybe we want to do something to stop climate change. What are the rewards that we could get back from trying to do something to take the temperature of the planet back to where it was a few generations ago when it was much more stable, much more close to what it was in pre-industrial times? Please.
Well, Miami might exist in 2100.
That is a great one. That's going to come up on the list in just a minute. We're going to call that sea level. So by bringing the temperature of the planet back, you're not going to allow sea level to rise. For those that went to MIT, by the way, there's some great signs up right now that talk about sea level rise, and they say that MIT will be under 0.5 smoots of water in the next generation. For those of you that don't get the joke, you can ask me later. Smoot is a person, so 0.5 smoots is about a half a person deep of water. They're re-engineering the green building, the building that I'm in right now, and they're worried about doing basement renovations because as sea level has already risen, the basement becomes more buoyant and it causes architectural problems. It's something that we're facing, but that's a great one. That's one that we would want to stop.
There's some interesting papers published by Zhang and company that I'm sure you're familiar with, looking at the effect of the Asian industrial particulates on precipitation in the Northwest. So what happens if we try this geoengineering and that contributes further to redistribution of precipitation?
So you're getting a little bit ahead of me, but I've got a slide to that effect. But I would say that that is one of the risks of this, which is that by doing geoengineering, you are going to have effects on the precipitation patterns of the planet. And that's absolutely true. So you've jumped to risks, and I actually have a slide that I hope will make you happy. But I am interested in rewards, and I mean, I can throw one out there, which is, it's the temperature, right? We're talking about doing something that returns the temperature to normal. So I'll just throw that out. That was maybe the most obvious one, but let's go on.
Okay. The temperature is in fact down, but you're living with more CO2 in the atmosphere, so your crops will be healthier. You'll get bigger yields in agriculture.
Yeah, we're going to talk about that one. So that one is often floated by geoengineers, which say that crops, obviously plants, are going to thrive on CO2. More CO2 must be good for plants. There's actually very little evidence how plants respond to increased CO2. There's some greenhouse chamber experiments on that. But that is a supposition. Same amount of sunlight, more CO2, higher crop yields.
Yeah, you mentioned at the beginning that the effect of particulates in clouds isn't entirely understood. So it seems to me the main advantage you would gain is you would gain in knowledge about how to tinker with the system before you're on the edge of the cliff. And, figuring out what could be put in and whether or not you had a linear region, those kind of things.
Yeah, you guys are both getting a little bit ahead of me, so I actually have a figure to that effect, which is great. But maybe I can change the wording around because this has been suggested, which is that maybe today we don't need this technology, but it's going to become critical one generation from now. And we're going to work out all of the bugs now in some controlled way. And therefore, when we really need it, we'll be able to do it. It hasn't been proven to me how you do this at a small scale and understand what all the bugs are.
Small changes, and then you have to project.
Yeah, so that hasn't actually been proven how that would work out, that you would have a big enough effect to detect it, but that you would also work out all of the bugs at the same time. Let me go to the back of the room. I think let's grab this one, and then we should go to rewards in a minute, but please.
Okay, so one effect is that warmer temperatures mean less snowpack, which means everybody like Chile and California, frankly, will have less snowpack and less to carry them through the summers. So cooling the earth down would increase snowpack, assuming nothing happened to the rainfall pattern.
Exactly.
And that could be a thing.
Yeah, no, that's absolutely right. So if you reduce the temperature, you bring things back to precipitation in the form of snow, which is snowpack, which is needed, especially in a lot of communities like this one. Absolutely. So I know that there's other ones, and we could probably continue this. I actually do this in class, and we spend about a half hour on it, so I apologize that we're going to spend 5 or 10 minutes on it. But how about rewards? How about risks? What are the side effects that you could get into by doing this type of thing? I should go for the host area over here real quick, just to earn my keep.
Some people may be old enough to know about acid rain. It seems to be with sulfur dioxide in the atmosphere at this level. Will have a tremendous effect on plant life.
Yeah, so most of the proposals are based on sulfur dioxide because we know that it's a strong scattering agent or sulfuric acid, and you're absolutely right, it has to come out of the atmosphere. So you're talking about raining 10 teragrams of sulfuric acid that wasn't there out every year. That's exactly right. please.
I don't know if that's a risk, but ocean acidification appears to be a problem, and this wouldn't address that.
That's exactly right. So for those that have looked into this, and maybe more importantly for those that don't know about this, CO2, you'll notice that Arrhenius called it carbonic acid, not CO2. The historic term for it was carbonic acid. When it dissociates, when it's taken up by water, it creates an acid. It creates acidification in that system. So the oceans are increasingly being acidified, and that's why coral around the planet is dying, is due to that acidification. So in this case, you're going to bring the temperature back to normal. You're going to let that acidification keep happening and actually rise possibly exponentially, and you would do nothing whatsoever about that. It's absolutely right.
During the Cold War, they used to talk about a nuclear winter. I guess that involves particles. It's certainly a bad idea.
That's right. I think I would rephrase that one as one of the problems that you could get into, which is that if you don't tune the system properly, you could go past the set point. And we'll talk more about that in a minute or two. Let me grab one more.
You have winners and losers, which creates political and diplomatic issues.
That is absolutely one of the other ones. So I'm going to do this very quickly just because I don't want to run out of time. I'm sorry that I didn't get to everybody. I would have loved to have talked to everyone about this, and we can do that afterwards. This is a paper that was written by Alan Roebuck in 2008 when some of the first suggestions of geoengineering were coming out. Paul Crutzen paper had come out somewhat earlier. He talked about rewards. Cool the planet, reverse sea level rise, reduce or reverse ice loss. I think you hit all of the top three. I've actually hit things that I think are very important. Cooling the planet and reducing or reversing sea level rise, I think are critically important things. I've put orange over here on some of the risks that I think are things that we really need to talk about. And I'll be honest with you, the things that I've put in red up here, you got a couple of these. There's a couple that were missed. I think for me are non-starters and why we don't do this. For example, in orange, the effect on plants that was mentioned, there's evidence to say that if you put particles in there, you get diffuse radiation, which is what we saw in that photo that I showed from Singapore earlier. Even though there's more CO2, plants don't grow as well with diffuse radiation. So you actually have a negative as well as a positive. And it looks like, at least from some of the studies, that the negative is more important. You reduce crops because of this. Acid deposition was caught. Lower solar power margins. I wanted to put an arrow on this because this was a clean tech series. I think we'll do question and answer afterwards, so if you don't mind. Lower solar power margins are really important for this series because if you have this diffuse radiation, you don't get the energy back from solar cells that you would before. So you start to do this and you become less and less capable of producing power from solar cells. And so therefore you are eliminating one of the replacement technologies that you need to fossil fuels by doing this method. I hope that makes sense. There's been a few really interesting papers written on that, and I thought it'd be of interest to this group because of the focus of the Clean Tech series. Regional droughts, precipitation was mentioned. The one that was missed was ozone depletion. I'll go back to that in a minute, but one of the things that we noticed after Pinatubo went off was that these particles were not just sitting nicely in the stratosphere and maybe raining out as acid rain. They were actually active sites for chemistry. They were chewing up ozone. The lowest ozone on record was the few years immediately after Pinatubo. We can talk about the chemistry of this if you guys are interested, but essentially those particles act as sites for CFCs, which you remember from the ozone hole days, to chew up ozone molecules, catalytically destroy them. And so this is a record from a satellite showing the ozone falling away at the same time as there were particles being forced into the stratosphere by the Mount Pinatubo eruption. So other issues, Mike just mentioned one of them. But there's other issues that were actually missed in this Roebuck paper. Does this undermine mitigation efforts? Do we say, hey, we fixed it. It's taken care of. The temperature's back to where we want. We don't have to worry about it anymore. We don't have to worry about getting the CO2 out. People worry about military use. There's actually a number of treaties that are in place that say that we are not going to mess with the environment. These were put in place because of Agent Orange during the Vietnam War. They're still in place and they cover things such as this. Early small-scale experiments that were planned in the UK were actually shut down because people realized they were about to violate treaties that they had signed. And the other one is who controls the thermostat? I think this is really interesting, right? What if Arrhenius controlled the thermostat? What do you think he would do with it? Right? What if you controlled the thermostat and you were in Saharan Africa? You might actually want it to be somewhat cooler than it was before. So this is a big question, who's going to decide that? So I mentioned ozone. Precipitation was brought up. So these are modeling studies. These are not real experimental studies. We haven't tried to do any of this yet. But these are attempts in models to understand if you did geoengineering with sulfate aerosols in the stratosphere, what would the temperature look like? They're trying to tune it back to the temperature that the planet was at before the industrial age started. You can see that the precipitation has fairly radically changed in some of these simulations. More precipitation in certain areas, less precipitation in other areas. There's winners and losers. Certain people become much drier. You create deserts where there weren't deserts before. You create forests, you create habitable land, crops in places that there weren't crops before because of this. It's not the thermostat that you're controlling the rain in this case. And so we haven't really worked this out yet. So maybe what I'll do is I'll just wrap up with a couple of quick postscripts as I see that my time is coming to a close. I think that this was mentioned, and so for me personally, this is one of the huge things that I see as a problem with geoengineering, which is that what we're talking about doing is manipulating climate with aerosols and the clouds that they spawned. We started out with this figure, and I said this was the obligatory figure that an atmospheric scientist had to put up during a talk, where we talked about greenhouse gases warming the climate, and we talked about aerosols and clouds cooling the climate. And so for my generation, we were very into our boom boxes and our stereo systems, which now we have iPods and iPhones and things like that. But these always had the sort of coarse and fine knobs on them, right? If you wanted to tune the radio, and you had sort of a coarse knob and a fine knob. And so geoengineering sort of strikes me in this way, that what we're suggesting doing is tuning the climate system back to where we want it, very precisely using the knob that we just acknowledged was the most coarse part of the climate system to begin with. I think it's very striking that the folks that are proposing this are not normally the folks that are doing the measurements of aerosols and clouds. In fact, I don't know anybody that's actually doing the measurements that are proposing geoengineering. It's the people that don't understand the uncertainty that are proposing this. I do have some warnings to issue, and these are the things, especially for the younger members of the audience, that's going to be very important to their generation. It's becoming impossible to say that climate change is not happening. We're seeing too many signs of it. We're seeing species migrate in addition to the temperature rise of the planet. We're seeing coral dying out, changes in ice pack, changes in the amount of precipitation that's coming down as snow. And as that happens, some groups are going to be looking for a solution to continue burning fossil fuels, to not change that part of our economy, but instead to find a way to stop the effect of that without actually stopping the process itself. The thing that's very seductive about this is that it comes at an extremely low cost. 20 teragrams of sulfur sounds like a lot, but people have calculated that if you have a few dedicated aircraft that are ferrying sulfuric acid into the stratosphere on a daily basis, that would be enough. Or you could build a garden hose that just ran up from a sulfuric acid production plant and pumped this material out. People have estimated that this may cost only in the tens of millions of dollars a year to sustain something like this. And so this is going to be extremely seductive. You're not going to have to stop doing anything that you don't want to stop. You're just going to have to throw in a few tens of millions of dollars a year. Industrialized countries don't even think about that in terms of that's the money that we don't account for that's in the noise, right? So it's going to be very seductive to do this. And people are going to have to make this choice if this is something that we want to pursue or if the risks are going to be something that are too high. For me personally, since this is my 2 cents and I'm the one in front of the room, I would say that those 3 red bars that I lined up are the reasons that I would never do this. I think that those risks are just too, or those, maybe I can say uncertainties of those risks, are just too large. Talking about messing with the Earth's ozone layer, getting rid of the protective layer for UV radiation, changing precipitation, those are things that I just don't think that we can mess with. The much clearer path forward, for me at least, is to take away the CO2 that we already know is in the atmosphere, the thing that's much more certain, the thing that we know we've put there, we can ramp down in a way that we've already seen that we've ramped up. That's the much more safer thing to me personally. I want to be clear, that's my opinion. Maybe it's a slightly informed opinion, but it's still my opinion. It's not a scientific result. So with that, I'd just like to close. I mentioned that I'm going to bring this talk back to California. So this is my group, a wonderful group at MIT right now. We're at a pizza place just around the corner. This little guy is a prospective group member. He's actually the son of one of the members of the group. But we've got some fantastic folks. Simon, who's in the picture, is working on the effect of ice clouds on aviation. You may have heard about ice taking down aircraft recently. That's one of the fun projects that we're working on. Ewen and I'll mention Shayna, both just recently left the group. They were working on different aspects of cloud formation, but they're moving right here. So Ewen just took a job with Los Gatos, who builds small instruments to do atmospheric monitoring in Mountain View. Shayna is moving to San Francisco proper this coming August and is going to be working for company Environ doing consulting. Sarvesh and Maria are current graduate students working on building equipment to do the types of experiments that I talked about, cloud chambers, as well as measurements to identify what particles are in the atmosphere. Kern is looking at some poorly understood formation mechanisms. Casey, I was just talking to Rolf about, is looking at past climate by looking at ice core records of particulate matter. And Alex is looking at how clouds affect, and this is the fun thing that we're just starting to work on is how clouds affect exoplanets. So that's something that's been in the news recently. As we detect these planets around other stars, we find that most of them have clouds around them, and it limits our ability to detect what the atmosphere of those planets is like, what the surface of those planets might be like. And so we've set up some experiments in lab to try to understand how those clouds form and how we might take them out of measurements so that we can peer through them and understand climates around other planets. That's a few years off. We've got to figure out climate change first. But still, it's a fun project to work on. So with that, I'd like to say thank you guys for your time. Thank you so much for the invitation and the chance to come out. Thank you, Ralph, for the suggestion. And I'm happy to take any questions. I'm sorry, I know that there were a few, and maybe we can take those now.
Thanks, that was really interesting. The particles that, the 20 teragrams that you throw into the atmosphere, are they of a size that could be of potential health concerns, pulmonary, cardiovascular-wise? And has anyone modeled what kind of concentrations you'd get in the troposphere over chronic periods to kind of assess if it's in a range that could produce health effects, given that we already have that going on at a local level?
Yeah, it's a great question, and that's something else that's been in the news recently, which is particles that humans emit into the environment are not only bad for climate, they change the climate system, they change clouds, but they're also bad for health effects. So a very high fraction of the amount of childhood asthma, for example, can be attributed to places that have high particulate concentrations. So if you go to the Ohio River Valley, where there's a lot of coal combustion, it's the highest particulate content in the United States. It's also the highest incidence of childhood asthma. I'm not sure how to say this exactly right. Maybe one of the good things about this method is that it doesn't actually it doesn't affect that. Although that's a little bit of a strange way to put it. It doesn't have that negative effect. And the reason that it doesn't is that the sulfuric acid is being put in the stratosphere. It's high enough above where people are living and where we're breathing that it transforms by the time it comes down to the surface. And what I mean by that is it's falling into the troposphere very high up, many miles above our head, roughly where air traffic's taking place. And it's mostly being scrubbed up by precipitation. So it's coming out predominantly in the form of acid rain. It's not going to be directly inhaled. Those are particles that are normally created close to the surface. So luckily, we don't have to worry about that part of geoengineering. So.
I'd like to hear a little bit about one other effect that I've heard about this particular technique, and that is that if you ever decide the side effects are so bad you want to stop, that you tend to bounce your temperature up much more rapidly than it would have gone originally, which puts lots more pressure on species. And I don't see anything about that in your risk and reward, but I've heard that's really important.
You're absolutely right, and thank you for bringing that up. So Alan, in writing this paper, actually did have that in the paper, and it's just sort of listed under other environmental side effects. But what we can think about is this. You're absolutely right. So say we take the temperature of the planet back down by 1 degree, but we continue to ramp up CO2. That means if we weren't doing this, the temperature of the planet would get warmer and warmer and warmer. At some point, maybe it would reach 2, 3, 4, 5, 6 degrees. And what we're doing is we're not putting in 10 teragrams of sulfur every year. We're putting in 12, 14, 16. Now we stop. Temperature of the planet doesn't go back to where it was now, 1 degree or 1.3 degrees warmer. It goes to 3, 4, 5 degrees warmer. And those particles come out rapidly. We know from the Pinatubo example that they come out in 1 to 3 years. So you don't talk about sort of gradually warming like what we've done over the last couple of generations. You talk about going from a pre-industrial state to plus 5 degrees in 2 or 3 years. We're already having problems, and there's a lot of people looking at adaptation being too slow to keep up with what's going on right now because it's unprecedented. Things have not evolved to change to CO2 changing this rapidly. I can't imagine what they would do to a temperature change like that. We can only guess, but that is, it's under this heading. It is in the paper, just to give Alan credit for that, but it's a complete unknown what effect that would have. Yeah, the system would snap to an incredibly new, different state.
There's this Danish guy that's argued that cosmic rays, really cosmic particles, have some impact on low cloud formation, and that has a reflective effect, on net cooling, I guess. But
yeah,
is that really? Actually, I asked Professor Manuel about it, and he said it's been discredited. But
that's putting it very mildly. Carrie's very politically savvy. So if you would like to stay later, we could look at this, and I put together a few slides on this. So we were talking, Greg and I, just before the talk about this. There is a paper, Svensmark. I'll try to give credit where credit is due. There's a Christensen and a few other co-authors on that, and I can give you the references if you're interested. But what these folks did was that they looked at cosmic rays, and they seemed to say that it was somehow correlated with climate. And they didn't really know how, so they worked on this later, and they said, well, maybe it's forming more clouds. And what they did was they took a very small part of the cosmic ray record. Cosmic rays, by the way, make ions in the Earth's atmosphere as they pass through the atmosphere. Those ions can help form particles. The ion acts as a stable site that other material can condense around to form a very small particle. So this is the theory that maybe that happens. And so they had a very small part of the temperature record, a very small part of the cosmic ray record. They said, oh, look at this great correlation between them. They picked a part of the temperature record that was about yay big and cosmic ray record. And so this figure that I'm showing right now is the cosmic ray record over a long period of time and the temperature record over a long period of time. So this is how it was discredited. Does anybody see a correlation between those two here? All right, so I think that they cherry-picked data, to put it mildly, and there were some folks that latched onto that as saying that there's a natural cause for climate change, but it just doesn't hold up to scrutiny. Unfortunately, in the last IPCC report, several scientists had to spend several years discrediting it, going through the data. This is just summing it up in one figure. I can go over the real summary later if you want to hang around, but yeah, that paper just doesn't hold water.
Can you comment on any attempts to reverse or slow down ocean acidification?
Yeah, unfortunately there aren't a lot. And I think that that's one of the big advantages of so-called carbon sequestration, removing carbon from the atmosphere, removing carbon dioxide from the atmosphere. The best way to not get ocean acidification by putting, quote-unquote, carbonic acid into the ocean is to not have it in the atmosphere or bring it down to the pre-industrial levels. So I think that that's one of the reasons that people are really trying very hard to do carbon sequestration methods, trap that CO2, put it back into used wells, put it into biomass, and then cover it up so that it doesn't decay. The geoengineering folks, and I've been to a number of talks, not surprisingly, because it's probably a good idea to keep an eye on this, don't talk about that. In fact, I've had some interesting conversations about it because you bring up, well, what about ozone? What about ocean acidification? And they say, well, that's not our problem. Hear me out, though. This is the argument. This is how it goes with the geoengineering community. They say, well, we're tackling the problem of temperature increase. It's not our fault that the oceans are acidifying, and it's not our fault that ice packs are going, and so on down the line. So they say that, well, that's not something that we really have to worry about because that's not what we're seeking to solve. This was not from me, it was from another interested member of the audience, and they said, well, isn't that like offering a drug that treats your headache, but it doesn't take care of the cancer that's causing the headache? And it's really true. Maybe it is tackling that one small part of it, but it's ignoring the larger Earth system, which is itself sick in that case. So yeah, it's a great question, but as far as I know, geoengineering does not try to tackle ocean acidification.
One of the concerns that climate scientists have is releasing the carbon that's in the northern part of the Canada and Russia and the Siberia. Do you see any hope of keeping that part of the world cooler if we had to?
Yeah, so there's a serious concern, or there has been a serious concern, that as temperatures rise, what we're doing is we're thawing permafrost, which is indeed the case. And there is vegetation there that is going to start to decay once you've frozen it. It's like taking the peas out of the freezer and throwing them on the counter. They're going to start to decay at some point. They've been trapped when they're sitting in your freezer. And that is going to release methane. And one of the things I mentioned is methane is the second most powerful greenhouse gas right now, the second most important one. And so the good news behind that is it looks like experiments are tending to show that we're towards the lower end of the estimate of amount of methane that's released from that decaying vegetation. This is work that's being done by David Archer at the University of Chicago. And so David has written a couple papers on that recently. But I think some of the early work was now what we consider to be towards the high end of estimates, the ones that were sort of catastrophic results. And so the more modern work tends to push that down to becoming less of a concern than the continued emission of CO2, for example. It's still a concern. It's still addition of greenhouse gases to the environment. It's just probably not as big of a factor, as important of a factor as the addition of CO2.
So how much do the clouds formed from particulates impact the local climate? Like, so if we switch from coal to natural gas, for example, will we change the temperature in our local climate, or how much is the system global?
Yeah, I was wondering if somebody was going to ask that question. It's funny, every once in a while when you put these figures up, there's this like sort of secret thing that you've got there, and you're wondering if people are going to catch you on it or not. So that's really an interesting point, because this is global warming going on. And if you look here, there's things that fall to the left of zero. It means that there are regions of the planet that have cooled at the same time that the globe has warmed. And one of the classic ones is the Ohio River Valley in the southeastern United States. And so this is a circuitous way of answering your question. But there are examples right now where there's more particulates that have been put into the environment than there is greenhouse gas addition to offset the cooling. And so there are regions that have actually cooled over time. So you are absolutely right. If we were to take particulates away, there are regions such as Southeast Asia, China, and India, which are probably staying relatively lower in temperature because there are so many particulates being emitted at the same time. Southeastern United States is a classic case of the particulates that are a byproduct of coal combustion. And there was actually a cooling that's been noted there over time. The classic one that I teach in class, which is really fun, depending on if you were in Eastern Europe after the fall of the Soviet Union or not, is that the temperature of Eastern Europe skyrocketed after the Soviet Union fell in the late 80s and early 90s because the economy collapsed and it shut down all of the industrial emissions, it shut down a great deal of the power plants, it took away all of the particulate matter. So this cooling, this regional cooling that they had because of particles went away. The temperature went up something like 3 degrees on average the following year. So in answer to your question, I hope that does it. There are going to be regions that would see an increase in temperature, a radical increase. It would predominantly be industrial areas such as Southeast Asia, China, India, places like that. But even some in the United States that experience that. So.
Yes, my name is Armin Nuckmans. I happen to work in geoengineering, not marine cloud brightening. And I'm not particularly in favor of this sulfur putting up in the air. But the description that you give certainly doesn't give justice to the people that are working in it and the consideration that they do. First of all, for example, the amount of sulfur that's being proposed putting in the air at the very most is 2 million ton, not 10. Okay, and that's a very, very small fraction of what's being put in the air already by the existing power plants and everything like that. The particles that you think, and somebody asked that question, there's 0.2 micron, the particles that accumulate in your lungs are on the order of 4 micron, things like that. And so many of the things that you list over there are up to negotiation. For one thing, most of the climate models cannot predict with any certain, any degree of certainty what the precipitation is. That's the most, and that's because of the clouds. And so this is one of the things that's not known at all. And what people, it's like these guys are doing this sort of hidden in a laboratory. This is all out in the open. It's discussed over and again. You can read this, what people are thinking. And the experiments that they're trying to do in this particular field, you're talking about kilograms of sulfur dioxide that they're trying to, in the first experiments. So, one has to weigh the advantages and disadvantages. For example, changing, changing the characteristics of the sunlight that come to the air, affecting the solar, the solar radiation. Was your shadow changed when we had the Pinatubo? No, it's a very minor effect, and it only affects actually those things that collect sunlight. It wouldn't affect your solar panels. So many of these things that you list there, frankly, are very much open to discussion, even though I don't particularly favor this method. But you should really put on the other side and not just quote Alan Robock, which I have a great respect for, but there are other voices too. Thank you.
So I respectfully disagree with your comment. I believe that I've made it clear that I'm not a fan of this. What I will say is that I very carefully pointed out that there are certain rewards to this as well as risks. In answer to your questions, though, I don't think that you're telling the complete story. For one, and on a very personal level, the question was asked about inhalation of sulfuric acid particles, and I was very clear in that answer to that question that that was not something that we should concern ourselves about. So I immediately acknowledged that that was the case. I have been to a number of these talks, and the reason that I respectfully disagree with you is that this work by Alan Robock from 2008 and a lot of these points are not brought up in geoengineering talks. The risks and the uncertainty are not mentioned in those talks.
All the time. They're mentioned all the time.
We must be going to very different talks, I'm afraid. The other thing is that, in order to get a Pinatubo type effect, you cannot do it with 1/10 of the amount of material that you're putting up. This is, the extrapolation is by the folks that are doing this. So I know that people have suggested using different particulate matter in different sizes, but I don't believe that any of that has really been worked out. If that has been worked out, I would be very open to seeing it, but I've been to dozens of these talks now, and I haven't actually seen that. So I would very much welcome talking about it more.
Okay, next question. I have a peripheral question about cloud formation and the possibility of fog harvesting, if you have any comments on that.
I'm sorry, say again, I did miss the last one.
Fog harvesting.
Oh, fog harvesting. Yeah, so the concept of trying to grab water out of low-lying clouds, especially in marine areas. I believe that this has really taken off. Chile was mentioned earlier as being a very arid region that has lost its snowpack, and the possibility to try to grab marine stratus clouds or fogs to do that. I have to admit, I don't know a great deal about those methods and how it would be done. You're absolutely right. It would be a geoengineering. It would be trying to grab back the water that you've lost in snowpack over the years and instead grab it from clouds at the current time. I guess I would mention I don't know what the climatic impact of that is, because what you would be doing if you could do it effectively, and I don't know about those technologies, is that you would change the radiative balance. So you would be taking away something that had increased albedo, it increased scattering, and you would end up with a very much warmer place as a result. So I think that there would be some side effects that would have to be considered in a case like that, if you could do it effectively. But yeah, I have to admit, it's outside of my area of expertise.
A couple more questions?
Please, you're the boss.
No, just go ahead. Get a couple more.
That's right.
So there are countries like China that are bringing online some huge number of coal-fired power plants all the time, and no matter what the EPA does or what Europe does, it's mice nuts compared to what the Chinese are doing. So what do you feel are the most promising technologies to help us reduce CO2 in the atmosphere?
Oh, yeah, that's a tough one. So I guess I have to preface this by saying that I'm not in the energy technology area. So what I do know is that current sustainable techniques, wind power and solar, are not going to be able to take over the capacity of power that's generated by fossil fuel emissions. I think the popular one that's being explored in the United States right now is addition of natural gas into our economy, or increased addition of natural gas, which has less CO2 emitted for the amount of energy that's produced. Unfortunately, it's become so cheap that it's actually priced out of the market, the renewable technologies like solar and wind. So that has advantages as well as disadvantages. In the current arsenal, there's a lot of problems with it. We just saw the Fukushima issue a few years ago, but nuclear power may be the only thing that we're capable of doing right now that could take over the amount of energy that we would need to produce. There's a joint program at MIT that's run by Ron Prin, and they're into this so-called wedge solution, which says that there have to be many things that are done at the same time. Increased renewables, possibly increased nuclear, increased efficiency, more efficient buildings, higher mileage cars, that we have to put all of these into play at the same time. So I don't know that there's one silver bullet. I don't think that there's one thing that's going to do it. We're going to probably have to work in all of these areas at the same time. And natural gas is the one that we're going to have to be careful about. We can't sort of be seduced by that as well, that it is lower in carbon dioxide, but that it, at the same time, prices out the things that we're going to need 20, 30, 40 years from now.
It's a lower potency drug.
In a way, that's a good way to put it. Yeah, it's something that you can wean yourself off of, but it's not the long-term solution. Yeah, it's not no CO2, it's just lower.
In the not so recent past, the Earth had an ice age 10,000 years ago. It's had a series of them over the last 100,000 years. And these are probably 4 or 5 degree Celsius changes in global average temperature. There have been times when there's been vast growth of trees and at the poles. Again, a rather small change in temperature from what's happened. And they've happened at times when human populations haven't been putting additional CO2 in the atmosphere. Do people have good understanding of what causes those types of cyclical changes that have happened in the past?
Yeah, it's a great question. And I think it's one that's often answered. What's different about what's going on now? There's been periods that have had similar and higher CO2. And what I can say is that the answer is the timescales that are involved. So the thing that forces climate, that forces ice age, are the so-called Milankovitch cycles, which are orbital mechanics, which goes back to some of the work that I did with spacecraft early on. The Earth being slightly further, slightly closer to the sun over long periods of time, tenths of thousands, hundreds of thousands of years, the axis of tilt changing, that type of thing. And so that's what drives long-term climate. That's what drives ice ages. And you can see the last series 4, 5, 6 ice ages that line up that way. What's unprecedented about what's going on now is the rapidity with which it's happened. So you're talking about an addition of CO2 since industrialization. So you can pick out a year. Some people pick out 1750. Some people pick out 1900 is when the rise took off. But you're talking about changes of the order of coming out of an ice age or going into an ice age that are going to have taken place in a series of decades or maybe a century, not over the course of 1,000 years. And that's why we have adaptation issues with species. And that's also the issue that we're having now with how climate is changing this rapidly, wildfires, that type of thing. So it's a great question, but so ice ages are worked out. What we haven't worked out, where we're in unknown territory, is the rapidity with which carbon dioxide is increasing and the effect that it's having on the environment.
MIT is not responsible for me. I went to Swarthmore and Stanford Business School. Stephen Chu, as some of you went to, heard a really interesting talk over at Stanford a couple of weeks ago, in which he said that we are playing Russian roulette with the climate, and we are adding bullets. So I went to a local gun shop up in San Mateo and bought, actually they gave it to me, a real live cylinder for 9 bullets in a gun. And I just offer it to your thinking, as I think it's a heck of a powerful analogy. Secondly, how many of you went to the MIT Business School as opposed to engineers? 1, 2. Have you heard of this report that just came out yesterday called Risky Business?
I was wondering. I'd asked her to send me the report when she finished at the
It's available online.
All right.
56 pages.
Let me make a suggestion. Let me make a suggestion. We have many interested people here. We have a few announcements to make, and we can let most of the people go. And the people who want to stay can chat with this fascinating guy up close and personal for a little while afterwards, okay? So if we could just take a break here, make some announcements, and then come back to Dan, okay? All right.